So the way a deep network model works is, say it takes an image of a cat, and it represents that image as a collection of abstract features. So there's maybe some part of the deep network that responds to, the cat's left ear, and another thing that responds to its eye, another thing that responds to its whisker, but maybe also sort of aspects of these scenes that are not at all apparent to people, either, sort of little sort of lines and other shapes like those that the model thinks are very similar to each other, even though people don't recognize them as similar, or pieces of the problem like the color of the background or the color of the top right corner that are in fact totally irrelevant to the actual decision-making process that we care about. And so, one thing that's important to understand when we're deploying these models is how they're actually representing the world and whether the features that they're picking up on are in fact the features that we want them to pay attention to when they're making their decisions. Historically, one of the main tools that we've used as a field for sort of understanding these features that models are learning is visualization. We say, sort of show me a bunch of images that you think are all very similar to each other, show me the aspects of this particular image that are most relevant to the decision that you're trying to make, and thereby understanding what models are doing. The problem with this is that it requires a huge amount of very detailed human effort, right? That a typical model is constructing thousands or tens of thousands or hundreds of thousands of these features, and somebody potentially needs to go through and manually identify what each of those things is doing. And so, in our work on generating natural language descriptions of these features, what we've been focusing on is starting to automate this process of understanding what it is that an individual network has learned, what it is that an individual feature is doing, to better assist with human users who are then going to audit those models or make decisions about whether to deploy them or not. And so what we've developed is a procedure that can actually take a big deep network and assign to each of the features that it computes a natural language description of what it is that that feature does. And once you have this sort of index of descriptions of everything that the model knows how to recognize or everything that the model knows how to do, it becomes a lot easier for a human user to then go in and say, okay, tell me whether this model is picking up on a particular feature, maybe some sensitive demographic feature, something that I know is irrelevant to my task, and more generally to sort of automatically surface aspects of model behavior that are surprising or potentially dangerous. So, for example, even thinking back to the sort of simple image classification problems that we talked about before, is this a cat, or is this a dog, or is this a zebra? We want models to pay attention to the thing that's in the middle of the image, the actual object that we're trying to classify, and not the context in which that occurs. This doesn't actually happen for free, and there's a lot of past research showing that, for example, if you ask a model to recognize a zebra, a lot of what it's paying attention to is the color of the ground on which the zebra is standing, and trying to figure out if this image was taken, in the savannah or in a grassy field or whatever else. And therefore, if you wind up with a zebra in a grassy field, models are likely to misclassify it. And so one thing that we can do is, using these natural language feature descriptions, automatically reach into the model and look for features that are specifically sensitive to things like the color of the ground or the color of the sky that we expect to be ultimately irrelevant to the decision-making problem that we're trying to solve.